Okay, so for ions, we will be making an ionic compound from, in this case, a metal and a non-metal. So we'll talk about this more with the naming, but in these cases, we are taking one element, one metallic element and one non-metallic element. And if we look at the periodic table, normally on tables that sometimes are colored in or shaded in, there's some distinction that happens kind of in the right portion, and we can kind of do this with this little rainbow line here. So there'd be like a kind of a zigzag or a staircase boundary happening here, which is going to separate the metals from the non-metals, and metals being on the left hand side of that, and then non-metals being over here. Right. So metals tend to form positive ions, and importantly, the first family or first group, the alkali metals, these are going to be +1, so that's important to remember. And then you have the second group, alkaline earth, those are going to be +2. Okay, hydrogen is interesting because it kind of falls in between. That's why in this table it's kind of shown floating around. It's like it doesn't really belong to a family, because it can have a positive charge that it often takes, but it's also considered a nonmetal, so it has some properties that kind of straddle both types of elements. But usually in acids, which are going to be important compounds that we go over, hydrogen will indeed be a +1. It can also be a -1, so I'll put a little slash here. That would be a more rare case, but that happens when it's paired with another metal, like sodium, let's say sodium hydride. Okay, on the non-metal side, we have basically starting, if you want to start from the halogen or group 7, we have this kind of family here, which is going to be -1. And then we have oxygen's group, -2. And then nitrogen, which we can do -3. Okay. So good to know these ion charges. Also, I'll add a couple that you can remember, which will help you with certain things. In general, the transition metals, which are kind of this block in here, those are going to kind of vary. So we don't have aren't good rules because they can vary. They can also have multiple different charges that are stable. So what you can remember though is that silver is going to be +1, pretty much always. Zinc's going to be +2. Probably seen this in lecture, I hope. And then aluminum +3. And as we kind of see from the other families and groups, how in vertical situations and columns, the charges tend to be the same. So you can apply that here. In other words, gallium underneath aluminum oftentimes is +3 as well. So kind of you can follow your intuition in that way, and that's if you're kind of stuck on something, that's usually what will help you. Okay, so going back to the problem, it's just a matter of figuring out what column each element is in. Potassium is an alkali metal. It's in the first column or first group, so it's going to be +1. Sulfur, you'll find right under oxygen, -2. So when you put those together, you want to make the overall compound neutral. And a common way or little rule that's used is if the numbers are the same, you just take one of each. But if they're different, you can actually do this little thing where you cross this. So if I bring this down, I would have K subscript 2 S, meaning there's 2 potassiums, which would give a total of +2 to match the -2. Okay, so for calcium and nitrogen, again, find the correct columns. We have +2 for nitrogen, sorry, for calcium, -3 for nitrogen. So again, if we write these here, if the charges don't match, again, you can cross them, so you should end up with this. Right, so this would be the correct formulas that you should write for these ionic compounds. So again, we're just kind of moving these numbers into subscripts. And that would make sure that the total positives equal the total negatives in this compound. Okay, aluminum +3, as we said. Bromide's a halogen, -1. So again, we have a +3 and a -1, and we would need to write it like this, using the same rule we've been talking about. Okay, hopefully that makes sense. The only thing I'll mention as a side note here is, let's say you had something where you ended up with something that was like a, as we'll see, like a +4 maybe ion, and then something here that's, you know, a -2. So if you cross those and wrote this, the only thing you want to do is then simplify it, because ionic compounds should always be written in the most simplified or most, you know, empirical formula, which is if you can reduce those to a lower ratio, you want to do that. So that's the only caveat to this crossing the superscripts into subscripts rule. And hopefully that makes sense. And you can then write any ionic compound that you need. Okay, so for naming, I'm sure you've hopefully already seen the rules laid out in lecture. On this handout, I have the rules kind of summarized if you want to look at those kind of bullet points. So I won't really spend much time talking about that. That's something that you should review and learn on your own. So I'll just kind of go through the process, how I would think about approaching, you know, the names of these things, and again, I think if you know, have already attempted this on your own, that's going to be the most effective. So if not, maybe just pause the video and try to work on these, and then you know, if you get stuck, you can watch as I go through. Okay, so we're going to have a kind of choice to make when we're naming. Is it ionic, or is it covalent, or is it an acid? And pretty much that's what you want to learn with the, you know, types of, like the formula, the types of atoms present. So definitely a metal and a non-metal is going to be ionic, as we said, or if it involves polyatomic ions. So this here is just a polyatomic ion that you're going to need to memorize, essentially, or you will memorize it eventually, but at least, you know, you start to kind of look at the list and be able to recognize those as being an ion. So if we have any kind of, you know, polyatomic ion, it's going to be ionic, as the name says. So that's definitely an indication. Also, if there's a metal involved, it's going to be ionic. So, you know, this is all signs here pointing towards an ionic compound. So we have iron, which is a metal. This thing is called carbonate, but we can't just say iron carbonate because we're missing something, and that would be the charge on the iron. So if it's a transition metal, that's when we need this, generally this charge in Roman numerals. So that's one of the criteria with the ionic compounds, is determining if you need to put the charge or not. Okay, so transition metals like iron generally going to have to include the charge. And how do you figure out the charge? So you use the charge of the other ion, in this case carbonate. We'd have to look up, or eventually you'll memorize this, is -2. So if there's only one iron, it has to be +2. That's where this Roman numeral 2, that's what that means. So we have iron 2 carbonate. Okay. For the next one, we have 2 nonmetals. So definitely 2 nonmetals is going to be covalent or molecular. And covalent / molecular. Okay, so as you hopefully have seen the rules with naming that, you might have to use prefixes. Generally, you do use prefixes, it's just not on the first element. So here we have, this is a different color, nitrogen. And then we have oxide, but we want to say monoxide, which is kind of monooxide, a little bit simplified into monoxide. So you'll notice that the mono prefix is only needed if it's the second one. So prefixes like mono, di, tri are needed for covalent compounds, but mono only on the second element. So write that up here. Don't use mono for first element. Okay. All right. C, CaOH2. So again, we have a metal and a polyatomic ion. So this is going to be ionic. So maybe again in the beginning, just work on classifying it, ionic or covalent, or maybe an acid. That'll help with then going about naming. So we have calcium. The anion is called hydroxide. And we don't need to specify the charge of calcium because it's not a transition metal. It's just a group 2. It's always the same charge. Okay, another ionic one here. We have cobalt. Phosphate. Do we need the charge on cobalt? Yes, it's a transition metal, so we're going to put a Roman numeral here. Okay, so this one we have subscripts, so we're going to go backwards. So essentially the 2 would be a +2 charge on the cobalt, and if we just verify, the phosphate is a -3, so we would have cobalt to phosphate. All right, here we have a compound with 2 nonmetals, oxygen and fluorine. So this is covalent or molecular. I'll do this one green again. So we can't just say oxygen fluoride, because if it's covalent or molecular, we need prefixes. And in this case, because there's 2 oxygens and 2 fluorides, we're going to put the di in front of both, dioxygen, difluoride. So don't forget the prefixes for these kinds of compounds where there's 2 nonmetals. All right, back to an ionic compound. Sodium is a metal. We don't have to specify the charge. And cyanide is the polyatomic ion here, Cn-. So it's just sodium cyanide. Okay. This one is a little bit of a kind of asterisk one. It's just a kind of a common name that you should know, which is hydrogen peroxide. So it's hard to kind of explain maybe that we don't name this like dihydrogen dioxide, because this would be considered to be, I guess, 2 nonmetals, covalent compound. It's just there's some common names that persist, and so this is named kind of like if it was an ionic compound, even though it's not really. So just try to remember this one. That's the point being, this is hydrogen peroxide. It's like the the person that went into the restaurant and the friend ordered, when the waiter took the drink order, the friend said, "I want some H2O," and then this person said, "I want some H2O too," and then when the waiter brought the drinks, the person died. So it's my little hydrogen peroxide joke. Be careful how you order your water. Okay, CuBr2, we have a metal, and we have a nonmetal, so this is ionic, copper, and the nonmetal is bromide. Copper is a transition metal, so again, we're going to need Roman numeral here. And if we think about the bromide with the 2 subscript, that would be reflective of a copper +2 ion paired with the bromide -1, so this is also copper 2. Here we have 2 nonmetals, so phosphorus trichloride. So we, again, don't need the mono in front of the first one, but we do need the prefix for the second one. Okay. NH4, 2SO4. So these are 2 ions. So again, polyatomic ions, you want to recognize those. Therefore, it's ionic. And the first ion is ammonium. Second ion is sulfate. Right, so ionic compounds, we never use prefixes. So this is not diammonium sulfate. It's just the name of the first ion, ammonium, the name of the second ion, sulfate. All right, and then here we have an acid. So generally an acid you're going to recognize by having hydrogen in the beginning. So it'll be something acid. And I would again recommend consulting your lecture videos, your lecture notes for kind of the types of acids and how they're named. But the main distinction that usually is taught is you can look for if there's an oxygen or not. If there's no oxygen in the acid, then it's going to be hydro something ic acid. And that something is just going to come from the stem of the ion, the negative ion. So bromine, hydrobromic acid. Chlorine, hydrochloric acid, so forth. Okay. Sometimes with this next one, it's confusing to distinguish kind of what kind of compound it is or maybe what's happening. But if you can recognize the metal, potassium, that's the cation, basically you want to split it there because there will only be one cation, one anion. So if we recognize the cation is potassium, then the anion is the rest of it, which is called dihydrogen phosphate. Should be on your list there. You can look up for the polyatomic ions. Okay, so again, this is an ionic compound. There's a metal, potassium, and then the anion, dihydrogen phosphate. For M, we have another acid, H something. And this acid does have oxygen. So what you want to learn with this is that if you can remember or look up the name of the ion of the acid, like nitrite, the ite becomes us acid. So actually, let me just write. Ite becomes us acid. So then we'd have nitrous acid. So nitrite becomes nitrous acid. And if it was an 8, that would become ic acid. So nitrate would become nitric acid. Okay, so if it has oxygen, then just base it on the name of the anion. So it's H and then some anion. That anion name will determine the name of the acid. Hope that makes sense. Again, the more practice you do, the more it'll sink in. So lastly, we have another ionic compound. Barium is the metal, which we don't have to specify the charge of. And then this anion is perchlorate. Okay, so there's some rules I can show you maybe off to the side here, which again hopefully you've seen before. But so you have something like ClO2 minus, ClO3 minus. This would be chlorite. This would be chlorate. Generally, the ates have one more oxygen than the ites. If you have one less oxygen, it's hypochlorite. So again, kind of focus on these like prefixes and suffixes. And if you have one extra oxygen, it's perchlorate. Okay, so if you kind of learn this whole pattern, basically, that would be the extent of anything you would need with like the whole range of possible polyatomic ions. Now, not every element's going to have this. So for example, for nitrogen, there's just nitrite and nitrate, but certain things like the halogens, chlorine and bromine, things like that, you might have 4 different ions that have oxygen, and the different numbers of oxygens correspond to the prefixes and the suffixes of that name of the ion. So again, if that makes sense, it's going to be a little bit of, you know, learning the rules, some memorization, but I think just repetition will help to, you know, get these to stick in your head. Okay, and then lastly, we're going to write the formula. So this, the only thing that would be maybe important to mention here is that you want to make sure that these are all neutral. So make sure compound is neutral. Meaning if you have potassium, that's a +1 charge. Dichromate, you probably have to look that one up, is a negative, well, the formula is Cr2O7, the charge is -2. So when you put these together, again, you need to have 2 potassiums, right? We're doing the kind of the crossing thing of the subscripts to make sure that the compound is neutral. So if you just write K, Cr2O7, that would be wrong. Okay. In the same way, aluminum +3, hydroxide -1. So we want to make sure that the compound has 3 hydroxides. So we'll have parentheses around the OH with a 3. In the same way, ammonium is +1. Carbonate is -2. So we need 2 ammoniums and then 1 carbonate. Strontium is a alkaline earth, so it's a +2. Acetate can be written actually different ways. So one way to write it is CH3COO- or C2H3O2-. So it actually doesn't matter which way you write it. You'll probably see it both ways. So let's do it this way for here. Again, this can be that, or it can be CH3COO2. Okay, lead +4, Roman numeral 4 means +4. Sulfide is a -2 ion. So again, if we write this as Pb2S4, we just want to simplify it to PbS2. These ionic compounds are always written in the most simplified ratio of subscripts. Okay, phosphoric acid, as we said, this is going to come from 8. So PO4 3- is phosphate. So therefore, when we put this with hydrogen, again, we want to make sure that this is a neutral acid. So we're going to put the H+ cation with the PO4 3- phosphate anion. And to make that neutral, we would need 3 hydrogens. So make sure you do that and don't just write HPO4. Okay, dinitrogen pentoxide, so a covalent compound or molecular. The prefixes tell you how many of each element to write. N2O5. Magnesium fluoride, we have another ionic compound, and we look at the charges, or if you look at them, that should balance out to that. Hydroiodic acid is the official acid of Hawaii, so HI. And these last ones here are just common, or these next two are common names. So methane, CH4, ammonia, NH3. You know, I'll just kind of put little stars next to these. These ones, much like water, we just use the common name, so we should know these as you'll see them often. And then hypochlorous acid, if we go back to what I mentioned up here with hypochlorite, right? So let's kind of think about this one here. That's going to be translated as an acid into hypochlorous acid. So if we just take the ClO minus ion and add an H plus, right? Since they're both +1, that's just going to be HClO. So that's our final one here. Again, coming from hypochlorite, hypochlorous acid. Okay, that makes sense. Keep doing your problems. The more you do, the better you'll get, as everything pretty much works.